Hello everyone, delighted to have the opportunity to present my research at ICRA 2024. I am here to introduce Adaptive Model Predictive Control with Data-Driven Error Model for Quadrupedal Locomotion to deal with the model uncertainties problem. Helping humans to carry payloads is a common and promising application scenario for quadruped robot. However, the payload's parameters are variable for different tasks, and it is challenging to model it online without extra sensors. And if not tackle it properly, the model uncertainties will have an adverse effect on the locomotion performance of quadruped robots. For example, as shown in the videos, the extra payload affect the behavior of a camel and our robot fall downs because of not dealing with the payload properly. To address this issue, we propose the controller of integrating a data-driven error model into traditional MPC for quadruped robots, whose control framework is shown in the slide. Our approach leverages real-world data from sensors to compensate for defects in the control model. Specifically, we employ the autoregressive moving average vector ARMAV model to construct the state error model of the quadruped robot using data. The predicted state errors are then used to adjust the predicted future robot states generated by MPC. By such an approach, our proposed controller can provide more accurate inputs to the system, enabling it to achieve desired states even in the presence of model parameter inaccuracies or disturbances. The proposed controller exhibits the capability to partially eliminate the disparity between the model and the real-world robot, thereby enhancing the locomotion performance of quadruped robots. We validate our proposed method through simulations and real-world experimental trials on a large-size quadruped robot. In this paper, an ARMAV error model fitted from sensor data is implemented in a MPC based on the linear single rigid body model to compensate for errors of dynamics uncertainties. By using estimated ground reaction forces as indicators to predict potential state errors, we modify the method to improve its performance in quadruped robot applications. The error model combines the SRB model to become a hybrid model, which then is regarded as an equality constraint in the quadratic programming optimization problem. The hybrid model, by using the historical data, can have a better prediction of the future robot states even under discrepancies arising from the control model. The autoregressive moving average vector model is a widely used statistical method for analyzing and predicting time series data. One of its key strengths lies in its ability to capture and predict periodic behavior. Given that the locomotion of our quadruped robots exhibits periodic patterns, the ARMAV model is well suited for error prediction in this context. The formulation of the ARMAV consists of autoregressive model and moving average model. In the prediction part, the K-step ahead prediction is based on the previous prediction values and history data. The residuals AT are updated in every step. In the modeling part, the estimated AR parameter phi and MA parameter theta are derived from the inverse function and initial guess of inverse coefficient I according to pure AR model. Finally, the order of the model is determined by checking whether the reduced trend of residual sum of squares follows the F distribution and the residuals of the model are uncorrelated. The simulation section compares the proposed controller with linear MPC in two cases. The case 1 has Group A and Group D. The control model parameters are accurate in Group A, whereas in B group, the mass of the model is set to 34.7 kilograms, but the real mass is 23.7 kilogram. The results proves that the proposed controller helps to bring the robot's state closer to the desired value and reduces the vibration amplitude of the body height in the two groups. The figure of ground reaction forces shows that the hybrid model helps MPC adjust the input for the robot to achieve more suitable values for such improvement. In the case 2, an 8 kilogram unmodeled payload is applied to the robot body. The results show that the proposed controller has a noticeable effect in raising the body height to the desired value while simultaneously reducing the vibration by 47.1%, and the robot with the baseline controller falls down after 30 seconds of trotting. The first hardware experiment is to evaluate the performance of the proposed controller in dealing with the variable unmodeled payloads. In this experiment, the payload from 5 kilograms to 15 kilograms is added on the Sirius belt during trotting in place one by one. Concurrently, the data of real robot states in the baseline controller and proposed controller are recorded to evaluate their performance. The upside figure shows 12 steps ahead of predicted values from the error model in Euler angles and body height, which are very close to the true values of the real-world robot. The table and downside figure reveals that the proposed controller exhibits improved state tracking performance for roll, pitch, and body height in comparison to the baseline controller. The second experiment is to evaluate the performance of the proposed controller in the robot's forward trotting. The videos show that the proposed controller enables the Sirius belt carrying a 20-kilogram unmodeled payload to achieve a stable forward trotting, where the mean of com height is 0.397 meters with standard deviation of 0.0011 meters. However, the counterpart with the baseline controller is unstable even in a 10-kilogram payload, whose mean is 0.369 meters and standard deviation is 0.0035 meters. The obtained results validate the effectiveness of the proposed controller in facilitating stable trotting for the robot, even when confronted with variable unmodeled payloads. The proposed controller can, to some degree, deal with the problems caused by the model's inaccuracy, linearization, and simplification in MPC. The hardware tests validate that the Sirius belt carrying a 20-kilogram unmodeled payload with the proposed controller can achieve stable locomotion performance.